Okay, let's start. Welcome everyone to the afternoon session in this IFIMAC Day. We will have three different talks on three different collaborative projects. And I'm going to mimic Christina. She made a point, and I want to make my point. I use my seconds. So just let me just address a small thing. So this IFIMAC Day is all about getting to know IFIMAC better from the inside. We are all inside IFIMAC. But let me tell you that there are people here today among us who has offered themselves to help us, to make us more understandable for others. So getting to know IFIMAC from the outside. So we have Laura that has been recording all the talks today. They will be in our YouTube channel. So I invite you to check later. Then Johannes, Pablo, and Ferry were taking pictures during the talks and also during the poster session, and they have been tweeting all day. So let's applaud them. And of course, there will be a news in our webpage about what we have been doing today. So I invite you to keep track of our own social media and to invite your people you know to follow us as well. Okay, so this was the point I wanted to make. And now let's move to our first speaker in the afternoon. It's Herko van der Meulen, and he is going to talk us about single photon generation in 2D crystals for quantum information.
Okay, thank you very much. So I talk about the project of single-photon generation in 2D crystals for quantum information. The outline of the talk is first to present the different work groups who have been working in this project, to make some introduction to the different aspects of the title, and to take out two compounds which we have investigated, gallium selenide, where we have used static strain, and hexagonal nitride, where we use dynamic strain to influence the emission of single photons. And I finish with conclusions. Well, to start with, the work groups are of the different departments in the physics. The Departamento de Física de Materia Condensada, Juan Blas Palacios was the principal investigator. Then the group of Rubén Pérez, working on the selenites, which I present here, and we in the Departamento de Física de Materiales, Snezana Lazic and myself, we did the experiments on the 2D single photons in gallium selenide and hexagonal boron nitride. Further, there was one postdoc position which was consecutively fulfilled by 3 persons named here. And apart from that, we had also cooperations with other groups, Pablo Ares with Rubén Pérez, in experiments on the hexagonal boron nitride, and the group of Felix Zamora, also in the experiments of hexagonal boron nitride. Apart from that, there are also theoretical support from Pablo Garcia Gonzalez. So to introduce quantum information, and quantum information is an interesting topic nowadays, where a lot of investigation is taking place, and there are a lot of aspects like quantum computing, quantum cryptography, and quantum communications. They all use as a basic building block the qubits, which in contrast to a classical bit, which only has 0 or 1 in the system, a qubit can take values from in between 0 and 1, having a superposition of those 2 states. And if you have 2 qubits, you can also entangle them. Well, these qubits are quantum systems, and you can realize them in different ways. One of them is using trapped ions, other superconducting currents, which is, for instance, used in the quantum computer built by Google. But those have only limitations because you have to live in a very isolated and extreme cold environment. Another way to make a quantum system is use single photons, which you can manipulate reliable, and you can have them travel long distances without affecting the quantum state. Well, those single photon sources have been investigated for various decades already, and some examples from these are the systems where they use molecules, single molecules, color centers, for instance, nitrogen in diamond, or quantum dots in semiconductor infrastructures. Relatively recent, also in 2D materials, this kind of photon sources have been discovered in, for instance, in tungsten diselenite and boron nitride. 2D materials are materials which are started with graphene and then took off in a very variety of materials that can be exfoliated in a layer of one atom thickness or one single cell thickness, depending on what kind of compounds you have. Well, the advantages of these single photon sources in the 2D materials is they are very close to the surface. Only one atom is separating from the outside world, which means that they have less effect of decoherence. Because, for instance, in a quantum dot, which is buried into a semiconductor structure, the quantum states can be lost through decoherence when the photon is traveling through the outside. And in these materials, also, we can control the surroundings, and they can be built through structures. Well, the wish to have these defects is to control them, to put them in a certain place, and to activate them at the moment you want them. So this is the motivation for this study, is to search these single photon sources in various 2D materials. And the 2D materials we are investigating are very sensitive to strain. And so we will investigate the strain, the intrinsic strain on these single photon sources, and using static strain to reform the material and dynamic strain applying surface acoustic waves. First, some words about the way to measure single photons. Single photons from a source are made into a beam splitter where they can either go to one detector or to the other detector. And then these detectors are detecting pulses in a function of time, and these are illustrated here. And then we measure the time differences between consecutive pulses in the 1 and 2 detectors. And now, if you make a histogram of all these different values of the delays between the photons arriving in the 2 detectors, you can see that here at 0, which is missing here, the 0, delay 0, there is a dip, meaning that at 0 time delay there are no 2 photons. So there are no 2 photons emitted at the same time. That means we have really a single photon emitted. This histogram is a representation of the correlation function, which is depicted here, and which really measures the correlation between the 2 intensities normalized by the intensity of the one and the intensity of the other. So the first element, the first compound we investigate is gallium selenide, and this investigation was inspired by a publication in 2017, where they measured single photon emission in this gallium selenide. It's monochalcobonite material, represented here 3 layers of this material. The explanation which they gave in this publication is that there can be a very small selenide inclusion which deforms the material, so there's a strain, and this strain can give rise to single-photon emission. The static strain which we are using, we're looking into, are strains up to a value of 5%. So it's 5% relative length change, what you will see. The first is an investigation by the group of gallium Rubio, which is depositing a flake of gallium selenide onto stretched under the stretched form of PDMS, and then loosening the stretch, and then this ripples in the gallium selenide deposited on top. And these ripples, you can see them here in the picture, are really quite pronounced. And so these ripples provoke an energy shift of the gap. And this is depicted in the center image, where you can see that between 1 and 2 extremes there is a shift of 1.2 electron volts, which is approximately a few percent in strain, which corresponds to it. So this material is very sensitive to strain. And some calculations also depicted that really for the 7 layers which they used in this flake, the energy of the band gap really shifts over this large distance. And this is represented in a publication here. Now the idea of provoking this strain and to provoke eventually single-photon emission, like in the publication we saw, is, well, let's put a very small particle, in this, what we will use is a sphere of 1 micrometer diameter, and then put a flake on top of it. And it's a kind of image like a sheet going around this sphere. And the calculations of the band structure show us that in this system we can expect very long-lived excipients. That is due to the specific valence band structure, which is here like it's a caldera type, so there is really no direct transition, but more indirect transitions, like an indirect excipients. But of course, 1 micrometer is very macroscopic compared to defects for emission of single photons. And so that's where the experiment started, where it's here depicted the position of sphere on material, then the exploration of flake on top. And in optical microscope images, it looks like this, where the dots here, circle around them, are marked, which are spheres below the flake. And this is an image of the luminescence, which is measured around one of those spheres. But this luminescence is an excitoluminescence. It's provoked by the deformation, the strain deformation around this sphere, although it's not single photon emission. But these materials we tried to investigate, and we did a lot of experiments trying in different spheres, looking for some small defects. And after tedious work in 1 or 2 of the dots which are represented here, we could find single photon emission. The single photon emission was originated from this point. And here are intensities which are really localized on this one. As you see, what's here is a micrometer scale. This resolution. Spatial resolution is determined by the laser spots of 1.5 micron on the sample. So this is where we could find single photon emission, and we found the emission of both an exciton and a bi-exciton, which is depicted here in the scale, the power dependence of the emission. So we can see that this is a little bit sublinear, and this is the double slope of the exciton. So that is really illustrating that this is a bi-exciton and this is exciton. This kind of exciton bi-exciton single photon emission has also been observed in the tungsten with selenite. And so the image of this system is where we have an exciton and the bi-exciton level, which is like a double exciton, so two electrons and two holes confined in a localized spot, and which can be recombined through different polarizations. For applications, this is a very interesting kind of configuration, because if in the system these two levels, which corresponds to different recombination paths, which correspond to different polarization, have the same energy, so if they are degenerate, we can entangle these photons emitted. The proof of the single photon emission is this black curve, which anti-bunching with a minimum at 0 time delay, which we measured when detecting the exciton peak here in this correlation experiment. The big surprise was that making the same experiment, only detecting in the double exciton, the bi-exciton, we measured the opposite, a bunching. And until now, we don't have really an explanation for this bunching effect, which was not seen before. Our problem with this sample is that after a very long search in different dots, these materials show degradation, and on cycling the temperature a lot of time. So this one was dyed the sample. And this is the point where we were just before the pandemic started. And so now we want to pick on where we stopped at that moment and look for new candidates for this single photon emission, and eventually see if this was just one shot or it's really some effect which we can explain. The second material where I want to talk about is hexagonal boron nitride. Hexagonal boron nitride is one of the materials which was also quite famous in this emission course on single photons, where it's known that defects in the material, this like here, can give rise to this single photon emission. So it's really localized on the defect. The band gap of boron nitride is about 6 electron volts, which is called in the UV. So all those emissions lines which you see here in 3 sections of the visible spectrum, all these lines, correspond to energy much lower than the band gap. We studied this boron nitride in its form in powder, and this powder was thermally expanded at 1000 centigrade. So that means that these peaks were activated by this thermal treatment. And also, this can be observed to room temperature. One of those, a few of those peaks at 10 Kelvin show here the anti-bunching which I showed before. And also they show here the polarization plots, which means that if they are very polarized, it's also dipole emission, but they are polarized in a random way. It's like you put the powder on a substrate, and so the orientation is completely random. And here also a picture of this anti-bunching at room temperature. So it's really up to room temperature can give rise to single-photon emission, which is very interesting for applications. On this material, boron nitride, we also applied surface acoustic waves, which was the work of Snezana Lazic. And these surface acoustic waves are produced in material of lithium niobate, where these contacts have been evaporated and produce a wave along the surface of the material, like depicted here on top. And this gives rise to a wave which has alternating tension and compression along the surface. And this tension and compression, and also a piezoelectric field, is transmitted to the material which is deposited on top. So in between these contacts, we deposited this powder of boron nitride, and we could see that in some of them, this peak, which is here present at absence of this surface acoustic wave, shows splitting when there is a surface acoustic wave applied. But this other one doesn't show anything. Here it is very important how the grain is attached to the surface. And really, the contact is something we don't have a real control. So some of them are in better contact and some of them are not. Here's a picture of this splitting. So this is splitting at maximum power of the radio frequency, which is applied to the surface acoustic waves. And this splitting in this case is 1.1 milli-electron volt, and we can go up to 2.5 milli-electron. This periodic strain, tension and compression, has an effect on the band gap. The band gap, in this case not it's a band gap, but it's a gap of the defect. So the energy differences of the defect are modulated by the periodic strain which is applied. This is well represented in some calculation, where you see the strain is at order of 0.05%, which we apply in this system, and the tension and compression gives the order of shift of the energy. What we can do also to apply this in a certain way is to synchronize, for instance, detection, where we can also only, for instance, only detect when when we are at the left side, or only detect on the right side, depending on which phase of the surface acoustic wave. So in this kind of phase detection, you can really shift the energy emission as you like between these limits. Now this work on hexagonal boron nitride was part of a bigger investigation where also other groups were involved. And here we see the high resolution images made by Pablo Ares of the kind of defects were present in this hexagonal boron nitride. So the idea was to try to identify these defects and possibly connect them to some kind of emission. This is three vacancies, so the 3 borons and 1 nitrogen missing, and this one is the one which we used in the calculation on the previous slide. where the nitrogen is in the boron site and the nitrogen is missing, so the vacancy of the nitrogen. In this image, these drawings of boron nitride are tentative because in this state pictures which have a very good resolution, but can only you cannot really detect which one is boron and which one is nitrogen. But this corresponds quite well with these kinds of defects. This defect was mentioned already by one of the first publications as the origin of this emission. And to finish off this, the calculations which were made by Pablo Garcia were calculating. So this one defect with the nitrogen in the boron site and the vacancy of the nitrogen, and the three missing and one nitrogen missing and one boron missing, and with the density functionality calculations, can we show that there can be levels inside the visible range giving rise to this emission, as two examples here. So to conclude, these two materials, gallium cyanide and boron nitride, show effects of strain. We have seen a single photon emission in this gallium selenide, and we'll try going on searching for more emission, more candidates for this emission. Boron nitride, we've seen that we can manipulate the surface concentrate the emission and make really a tuning in the certain limits for this boron nitride. What we want to do in the future is to improve the contact, really make the boron nitride in some way fix it to the surface, but we control the contact, and to also to put other kind of 2D materials which show single photon emission on substrate for applying superconductive equation. And to conclude, these are the publications related to this work.
We have some time for questions. Is there any question?
Thank you for your talk. So you show an experimental image where you see the photon emission. So how did you get this image? How do you measure the photons, emission of the photons?
How do I measure the emission of the photons? Well,
you show an image, you say photons are here around.
well, we measure this in a spectrometer. It's a micro PL. Sorry? This one, for instance. This one. This is an intensity. So this is composed of a square inch of 16 or 16 or something like that.
But is this process going to excite something, or is
Yes,
just
you excite with a laser.
okay?
Excite the laser with a higher energy, and then detect the emission of the material.
In the emission, it looks like the G2 for long delays went not to 1 but to like 2 or so.
Yes.
Right?
That's right.
Why does it come from?
Okay, here we go. Yes, that's correct. The emission, let's see. I'm sorry. For instance, here we have two. This is due to a third level, which is also playing a role in the recombination. So if you take this plot and you plot it on very long times, you will do
The last question.
Yeah, maybe I did not catch it, but do you use HDN? The HDN that you use, is it single crystalline or is it powder?
It's powder.
It's powder. And do you expect some difference in a single crystal, or are you?
The single crystal is maybe 2%.
Okay, let's thank Herko again for the very good talk. So we move now to the second talk. Okay, our speaker is Pedro J de Pablo, and the title is Viruses as Molecular Containers, Transport Delivery, and Nano-reactors. Challenges and...
Can you hear me now? Okay? Yes? Okay, so in this talk, I will try to explain you what we perform with experiments with atomic microscopy, fluorescent microscopy, theory, and viruses. And actually, this is a nice story because at some point I thought that I was working at Autónoma alone with viruses. And then I found some people, in this case, theoretical people, that also were interested in viruses. And this was thanks to the collaborative projects. So I think these projects are very nice because they engage different points of view and different expertise in science. Okay, so I have to say that in favor of the collaborative projects. Okay, so in this project we are involved. Well, it happened in 2016. I think this was the first, one of the first, probably Rubén, maybe I'm mistaken. This is the first time that this collaborative project were awarded. And the participants were José Ortega, Rafael Delgado, and myself. Okay, as experimental. So we are two theoretical groups and one experimental group. So I will try to give, in this story, I will first make a brief introduction to viruses, because I think this is the second talk today about soft matter. First one was given by the Aragonés, so this is probably the second and also the last one. So this is also, viruses can be considered as soft matter. So we are like a rara avis in the department, as one is saying. Okay. So first I will make a brief introduction to viruses, and then I will try to make to explain the two published histories that are coming from the project. Maybe some time after the project was awarded, but they are there. And then finally I will talk about ongoing and future collaboration. Okay. In this case, I want to stress two projects, which is the Human Frontiers and also the IFIMAC project. You will see. Okay. So what is a virus? Well, virus, if you want to make a short answer to the question, is just a shell made of proteins or lipids or whatever, and inside you have the cargo, and the cargo used to be probably genomic cargo, can be single-stranded DNA, double-stranded DNA, etc., whatever. Okay. So we are going to explore in this project several parts of the viruses. The first two parts are related with the viruses as alive entities. Well, they are not alive, of course. Well, who knows? It's an agreement with this thing. But the point is that one of the things happening with viruses is that they have to diffuse and go to the attachment on the cell. Okay, so this is, we can call it like the transport, diffusion, traffic. So all the three things are happening at the same time. And the second thing is delivery, and delivery is happening right there at the nuclear core. So when the virus is reaching the nuclear core, it's releasing the DNA for starting infection. And actually, this is what happened right here. And as you see, you need the virus to be more or less intact, more or less disrupted to release the DNA. Okay. So viruses, here you have a catalog of few viruses. They are huge, they are small, all kind of things. Okay. So usually they show microcellular symmetry, as you see here, and the typical techniques you use to explore the structure of viruses is X-ray and electron microscopy. And these techniques, they share in common that they use a lot of viruses to take the average structure of the system. So you have to make a heavy average of the system. You have to have thousands, millions, crystals of viruses in order to get what is going on. So from this thing, you can extract the relationship between the structure and the function of the virus. However, there is something else going on. There is something else you can measure, which are the properties, because you can engage the properties with the structure and the function. Okay. So these properties, when you are measuring thermal stability, mechanics, electrostatics, vibration, you say that this thing is physical biology. Okay. So in a sense, our group or our project is devoted to physical biology, to the physical properties of viruses. Okay. So another important thing about this project is that in viruses and in biochemistry, a lot of times you are measuring a lot of particles, a lot of molecules inside the test tube. And when you have a lot of particles, we are talking about millions and millions of particles, you are measuring the average behavior. And they have an asynchronous behavior, and also you get the average result. So you see this kind of response. However, we are interested in getting this. So we are going to make single molecule experiments. So it means that we are going to measure a single virus and try to understand what is going on in the single virus. Okay? So we are going to focus on this. And how? We are going to use atomic force microscopy. Also, fluorescence microscope that you will see later on. But first, atomic force microscopy. So we are going to take the white cake and pop on the virus. Okay, just scan and check them. So actually, in the past, we already explored several properties of viruses, such as internal pressure or static properties. Okay, that's some years ago. So we are going to use atomic force microscopy liquids. So we put our viruses in the liquid cell, we submerge the tip and the viruses everything together, and then we can explore the viruses in buffer conditions, where they are happy. Roughly. So here in this graph, you see a rough comparison between the cantilever size. This is a typical AFM cantilever, and actually right there you see the AFM tip. So probably it's right there, maybe the AFM tip. Okay, so it's very sharp, and each one of these lights is a virus which is emitting fluorescence. Okay, so still the virus is about the half size of one of these lights. So the virus is something very, very tiny compared with the massive cantilever that we are talking about. Okay. So let's go now for the first topic, the first thing that came out from the project and was published, which is about cargo delivery. Cargo delivery is about, in this case, how the human adenovirus is released in the genome. And something is known, if you see in this little graph, you see that the virus is going through the cytoplasm and is losing some parts of the virus. So it's just like ripping apart. Okay, it's losing some parts of the virus. And the parts that are lost here are the pentose. What are the pentose? Pentose are the proteins which are at the corners of the cosine. Okay, so the virus, in order to be infected, has to lose first the pentose in order to reach the nuclear pore. Okay. So something is known is that the pentose are the origin of mechanical stress. So in this red color, you see that the pentose are stressed. So they are experimenting mechanical stress. So they are like a weak part of the virus on one side. And the other thing we know is that the pentose release is happening in a stepwise manner. It's something we figured out a few years ago, that you are not losing the pentose all of them at the same time. You are losing step by step. So one pentose, two pentones, three pentones. Okay. So considering this, the question we make in this project is what is the dynamics of pentose release in human adenovirus? So we have to consider what is going on with virus inside the cytoplasm. So here you see one of these guys, one of these human adenovirus, which is pulled by the kinesin. This is a kinesin motor which is working on our microtube, and it is reaching the nuclear core right here. So it is known that the kinesin power strokes is about 2.5 kV. And also the virus has to go through all the molecular crowding which is going on inside the cytoplasm. And in this molecular crowding, and also because the kinesin is losing the pentose. So you see all these little red structures are lost through the travel to the nuclear core, and then finally the virus is reaching the nuclear core to release the DNA. Okay, so if you consider what is going on with the AFM, we can apply forces as low or works as low as 10 kVt. So if you consider the comparison between 10 kVt and 2.5 kVt, you see that we are about the same value. Okay, maybe a little bit more with AFM, but we are in business. What does it mean we are in business? That we have like a workbench where we can test the virus in the same conditions that they are in the cytoplasm. This is important because we can make in vitro experiments. Okay. So actually we are going to use the AFM, in this case like this hammer, just for poking the virus step by step. And actually this is what happened in the real experiment. So this is a human adenovirus. So you see what we are taking about 10,000 force strokes of about 100 piconewtons in the virus. And you see that first the virus is losing the pentose, and after a while, the genome in yellow color is spilled out. Okay, so as soon as you break the pentose, the exons are gone, and then the genome is also ejected. So here we have sort of like an in vitro infectivity process. Luckily, there is no biologist here, so I can say this. So, as I told you before, we are losing the pentose. So here you see in mark the 3 pentose which are gone. And in this experiment, we are interested in knowing how much energy we do have to apply to remove one penton on the one side, and on the other side, we are interested in knowing the transition rate, okay, to lose one penton. So here you have the 2 quantities we are interested in. This is the reaction coordinate, this is the free energy. And here you see the penton in red color, which is copper, okay, because the AFN. So when you make a cumulative graph of the probability of losing a penton, you can do, for instance, this graph for 100 piconewton, and you see that for 100 piconewton, you lose most of the pentons after 40 frames. Okay, so this is a kind of way to understand what is the probability of losing the penton after you have invoked the viruses during a few frames. And actually, you can measure several forces. Instead of using 100 piconewton, you can use from 100 to 250 piconewton, and you can fit this probability to the Weibull analysis. In the Weibull analysis, there is an important parameter which is beta. What is beta? Well, beta is a parameter that when it is minus than 1, it means that you have the Linde effect. What does it mean, Linde effect? It means that the failure rate decreases over time. So the longer the time, the less probability of losing failure. This is what happened, for instance, in ancient monomer. Okay? You can have beta equal to 1. If beta equal to 1, you have Poisson process. Poisson process means that the failure rate is constant over time. Okay, no, this is the most useful. However, you may also have beta larger than 1. When you have beta larger than 1, you have aging. Aging means that the failure rate increases over time. Okay, so the probability of losing one penton is increased if other pentons are lost. So it's important to consider what is going on here. If this is a power stroke of the AFM, it's taking place during a few milliseconds, as you see here. So, an indentation is less than 1 nanometer. So you consider that the typical relaxation time of the virus is about 100 picoseconds, which is the normal mode of operation of viruses, and the AFM power stroke is 10 milliseconds. It means that the virus is always at the equilibrium. Okay, so the virus only, so this can be considered as a Markovian process where each state only depends on the previous one. So the memory has not, the virus has no memory about what is going on, just about the last event. So by making some, you can fit then use the Bell's equations to see something about transition state theory, and you can calculate, for instance, the transition without and with AFN. So when you apply the AFN post work, you are decreasing this energy barrier, and then it means that then the probability for the pentons to leave the virus are high. And actually, this is nice because then you can measure the transition probability for each penton. You consider the order of the pentons that they are leaving the surface. And here you see that the probability of leaving the first penton is this quantity, 2.7. Here is 4.7, and here is 6.4. And what do you see here? What you see here is 80. Means that the probability of leaving the penton is increased as the first penton has been lost, the second one is 4.7, and the third one is 6.4. So the probability of leaving the structure of the virus is increased. Okay, so what is the, and also another important parameter is that you can calculate what is the delta G. Delta G is the binding energy of the penton to the virus. In this case, we find it's about 30 keV. Okay? So you can know how much energy you have to apply to unbind the penton. So what are the biological implications? Well, biological implications are important because if you consider what happened with aging, with this process of increased probability of losing the pentons, you see that the first penton is lost after 20 minutes, the second one after 60, the first one after 60 minutes, the second one 30 minutes later, and the third one 20 minutes later. So you see that the pentons are leaving the structure very fast, faster and faster. However, if you don't have aging, then the probability will be independent from each penton, and then you will see that you will have 60 minutes here, 60 minutes here, and 60 minutes here. And is this important for the cell? In principle, yes, as you will see, because if you don't have aging, then the virus will get to the nuclear core very intact, without losing a lot of pentons. And then the genome will not be able of going through the nuclear pore because it's still retained inside the virus capsid. However, if you have aging, then the virus is semi-disrupted, it's almost destroyed, and then the genome will be able of going outside, okay, and leaving the virus and going to the nucleus. So this says the biological implications are important. And actually, we can understand the aging process in this case as a fine-tune of the uncoating process, which means that it's happening about 50% faster than without aging. And actually, this paper was selected in Physical Review X as one of the major works in 2021 in software. Okay, so according to the editor, this is software. Okay, so we are happy. Okay, so now the next topic, I will tell you about another topic of the project that also took a while, which is about the study of nanoreactors. In this case, we study electromechanical photophysics of GFP. GFP is the green fluorescence protein. It's a protein which is emitted in green color, or just like in blue, okay? In viral cases. So, in principle, in viruses, instead of having genome, you can also store inside some other molecules. In this case, for instance, GFP, you can store other kind of molecules, whatever. Okay? So, in this case, the virus is important for material science, not for biology. Okay? So, why is it important to have this kind of system? Because here you can simulate the molecular microenvironment of crowds. So inside the cytoplasm, you have a lot of people going back and forth, which are bouncing back again and again. And of course, the proteins working here are going to work in a different way than if you analyze only single protein. So it's important to have systems where you can have the crowding conditions more or less controlled. I'll tell you more or less because you will see. Okay? It's not always as easy as supposed to be. So in this case, we are going to use an easy nanoreactor. Okay, in this case, the nanoreactor is packing, in this case, a green fluorescence protein, which is emitting green light. So you excite in blue color, and you get the signal of the protein in green. Okay, and this work was made in collaboration with Professor Trevor Douglas of the Bloomington of Indiana University. And in this case, this is the result. Here you see the protein cell of P22, and inside you see the GFP, which is attached to the lumen of the virus. Okay, just an internal part of the virus. And actually, they put about 220 GFPs, which means that the distance between GFPs is about 200. So these GFPs are really crowded, are really close one each other. Okay, they are very close in a crowded situation. So we want to explore the fluorescence because this is the nanoreactor is giving us fluorescence. So in order to explore fluorescence, we are going to use the combination of atomic form microscopy and fluorescence microscopy. Why? Because with atomic form microscopy, we are going to change the microenvironment of the GFP. We are going to change the conditions, the crowding, etc. And with fluorescence microscopy, we are going to see how these conditions, how these changes are affected to the vision of the GFP. Okay, so we need a combination of both techniques. And actually, we built this system at the UN. Okay, it took a few years, so because it's something difficult to do. And here you see one of the first results we obtained, where you see a correlative image between AFN and total internal reflection microscopy. Here you see, you can count viruses here, and here you can see the fluorescent signal at the same scale. Of course, it's wider because you have the diffraction part, the diffraction limit. Okay? So, the experiment we're going to perform, we want to approach the AFN tip to the virus capsid, okay? And then in black color, you can see the force curve, and in green color, you can see the light signal. So it's important to remark here that our system is working simultaneously. You can measure at the same time fluorescence and atomic and force, because in other system, in the commercial system, you have to make a correlative measurement. You have to measure first AFN, and then switch off AFN, and then measure fluorescence. Here, you can do the two things at the same time. So I think this is important to remark. So then you see that in this corner is when the tip is touching the virus, and the light remains roughly constant. However, the light starts going down as soon as you start breaking the virus. So when you break the virus, the light goes down. And actually, when the tip releases the virus, the light recovers the original value. And actually, you can see in this movie, you go to the green arrow, and you can see that this light switch off the light during a while. Why? Because we are poking at this particular virus at this moment. So you see that the light is going down, and then when we release the particle, the tip is going up. So there is no artifact. It's just this is just happening at the values we are talking. Okay. So we use two kind of tips in order to check what is the change of the microenvironments. We use isolator silicon nitride and gold cover tips. So this is what happened with the case of silicon nitride. This is what happened with gold. With silicon nitride, you see that when you touch the virus right here in this corner, nothing happens, as I explained before. However, when you start breaking the virus, you start seeing the steps of the force, which means that you are breaking the virus. However, in that moment, you see that the light starts going down. However, in the case of gold tips, you see that the light starts going down well before you touch the virus with tip. So it's happening before. You see that this red line is marking you the place where the light starts going down. Okay. So actually, you make some statistics. What you see is that the silicon nitride, you need to indent the virus about 20 nanometers in order to see quenching, in order to see that the light is removed. However, in the case of the gold particle, of the gold AFM tip, you see that it's happening at a distance, at an indentation of -40. -40, of course, means that the tip is 40 nanometers away from the virus. So this is happening at distance. So you don't need to establish, you don't need to break the virus in order to quench the virus at this situation. Okay? So this is telling you a difference. So in order to deepen in the difference, another experiment you can do is to check how it's changing the quenching. So the quenching is the reduction of light as a function of the virus integrity. So here we are destroying the virus in a more or less controlled way, knocking the virus sequentially, okay? And here you see that what happened with gold tips and with silicon nitride, you see there is a gap. So the conclusion here is that with gold tips, always quench the process, no matter the particle disruption, okay? So it means that we have kind of electronic quenching here. However, in the case of silicon nitride, the tip quench process only when the particle is not very disrupted. So it has to be more or less intact in order to have quenching. So this is telling you there are two mechanisms of quenching. In this case, electronic quenching, we propose that is related with the surface plasma, with the coupling between the surface plasma resonance and the emission of the GFP. The tips are very close. Okay, so this is what we propose is happening. And the mechanical quenching is happening because there is some kind of GFP unfolding. And actually, it's a nice paper published in PNS where they check that as soon as you unfold a little bit the GFP switch off. So actually, this is what we propose is happening in our system. So when you make a simulation with all the GFPs inside, what you see is that some of the GFPs are, of course, undergoing some unfolding process. As you can see here, inside of the red process. Okay, so the GFP is aggregated, and there are about 10 GFPs unfolding, and then we have the light is switch off because of these GFPs. So we got accepted this paper recently, small, okay? And now, for finishing, I want to go to ongoing and future collaboration because of this project. And the first one is the Human Frontier project that happened 1 year later of the collaborative project, which is to explore also mechanical properties and all what's going on in virus cages. And also we got this IFIMAC project, which is about exploring the interaction between materials and viruses. And actually, in the case of Human Frontiers, I want to remark that, for instance, in this case, the simulations are able to understand what is going on with the cargo inside and what is going on also with the disruption of the virus in real time. So here you see in this simulation there is a crack, and then the genome is going outside from the cracked particle. So actually, this is what happened in the experiment. This is what we want to understand. Okay. And here you have experimental curves, and this is theoretical curves. So apparently, we are working to something. We are trying to match those things. The second approach is in the project IFIMAC is to try to understand the trapping of viruses on the surface. And we are now trying to understand this by following the language isotherm to extract to know the information about what is the equilibrium constant of viruses trapped on the sources. Okay? And this is the first experimental results we obtained, for instance, with human adenovirus and also with coronavirus in this case. So we are trying to check the difference between different materials, such as HOPG, or mica, or glass, etc. Okay? So other project ongoing with TFL, Lucas Fernandez, is to try to hear in viruses. So we put the tip on top of the virus, and we try to hear the resonance of this tip, and try to understand what are the vibrational modes of viruses, and try to see what kind of information can we extract from the cargo of the virus by using this experimental approach. So here is the summary, and I want to thank you for your attention. I am open for questions.
Okay, I will speaker doesn't need the microphone, I do. So let's go with Laura.
Thank you for the very nice talk. I see that in your DSP, you see you have a hydrophobic tail attached to the GFP. Is this the natural form of the GFP, or is something that you need to make it bond to the virus?
You're right. I mean, you can plug molecules inside viruses in two ways. You can make it in a way that you trap things just by assembling the virus, which is not very convenient because you trap maybe a couple of them. But the other one, as you say, is you prepare a fusion between the protein and the GFP, which are fused to the co-protein, and when you assemble the co-protein, then you assemble also the GFP.
Thank you. Yeah.
Then there was another question over here, and then Alberto.
So when you switch the virus, I mean, the emission came back after removing the chip again. Does it mean it's not really broken, but just kind of switched together?
I mean, the virus is completely broken when you push it 3 times. If you push it, let's say 5, 6 times, then the virus is completely destroyed. But for the first couple of times, the virus is able to recover the state.
The virus bleach, basically. So.
Thanks, Pedro. I had a question about the cargo release of the adenovirus. What is your speculation about the implications of the findings for the in vivo release? Because I understand that they should be stable outside of the cell while they become unstable inside the cell. So what is giving this mechanical instability inside the cell? And if it's crowding, which was my guess, why do you think it's so? Because, for instance, in the case of protein folding, sometimes it's a machine that it actually stabilizes protein. So I have a question. What is the speculation about that?
Well, the speculation is that it is known that if you have a virus, a mutant, which is very stable, then the stability is so stable that it's not able of being disrupted, and then it's not able of releasing the gene. So you need to have the virus in an unstable state, which is good enough to release the genome, but also good enough to keep the genome together during traveling to the nuclear form. So there is a compromise between stability and stability. It has to be right in the place in order to release the genome to the nuclear form.
We found that the time to release this, I don't remember the name of the genome, so the phantom, so the aposis was decreased. But the binding energy was constant. It's not the virus, it's a local binding energy. It's only determined what is happening at the aposis, or when you, it's not an influence if you are breaking already.
No, that what we found is that the binding energy of the first penton, about 30 kVt. So the binding energy of the first penton is about 30 kVt. The second is smaller, 1 kT less, and it goes down. Yes, and that's really directly with the escape rate. I mean, delta D and escape rate are related. That's why the second goes faster. No, the binding energy is for the first and the second are lower.
It's 1 kVt less, so it's changing from 30 to 27.
Yeah, but in terms of time, it makes a difference. Yeah.
Okay, so let's finish here. Thank you very much for the. We move now to the last talk of the day before the concluding remarks. And our speaker is Hermann Suderow, and he is going to talk about visualizing, understanding, and controlling Andreev bound states down to atomic scale.
Thank you. So I will try to use a microphone. So, okay. So I'm very glad to be here, and I would like to thank, of course, the previous board and the present board for giving us the opportunity to work in this frame. And well, I'm trying to explain to you what we have been doing during this year, and I'm trying in particular to explain to you what we have been learning during these years. And thanks to the collaboration, and maybe in this process we can see how this proceeded. Okay, so the work which I'm going to do here, there are two main protagonists. One is Edwin, who is sitting around there, and the other one is Subun, who has been around here. And this is a collaboration which was by several people of the IFIMAC, in particular Alfredo and me, and also other people. And we have been also working with people outside the IFIMAC, as I will show you in detail later on. Okay, so but today the protagonist is IFIMAC, of course, and let me try to show you what did we learn. So when we started, it's actually, you can take a look on Google Scholar. Here I just take two examples, Alfredo and mine, a list of co-authors, and you can see that although the same happens with other people who have been taking part in the project, although we have been working on things which are quite similar, as you are going to see, there were no really any connection between both of us. And of course, the idea is to try to establish such a connection between the IFIMAC project, which is now established, I believe. Okay, so I'm going to make a general introduction to superconductivity and then go to the place where we have found our common goals, which is Andreev reflection, and then show you what are the results which we have been obtaining. So why should we work on superconductivity? Of course, you may take a look on what happens next time you drive to Japan or you fly to Japan. You may be able to, instead of taking the Shinkansen between Tokyo and Nagoya, you may be able, if you are lucky, maybe in 10 years, to enter a superconducting train who is flying at 15 centimeters on top of the track, thanks to a technology which is really unique and which you can only use by using superconductors. So there is a helium liquefier on board, and the whole thing works, and it's already working for 40 kilometers, and it will work for even more very soon. Of course, superconductivity is also useful for quantum applications and for nanoscale science. And very recently, these gentlemen, they proposed a challenge, for a technological challenge, and they realized, these are gentlemen from Airbus, they realized that actually it's going to be impossible to fly using kerosene very soon, because it's not good for the environment, and the only solution is to use liquid hydrogen. So they want to change the whole design of the airplane by putting here liquid hydrogen tanks which are 20 Kelvin. So this is a process in which we are working together with them, because essentially we are one of the few people where you can understand material science, where we think we understand a little bit of material science at low temperatures. So the challenge is very big. So in the past 10 years, there have been more than 300 vessels which were made in order to carry liquid gas. So this technology goes at 100 Kelvin. So the thing, all technological aspects were already known, because liquid hydrogen is kind of known. In liquid nitrogen temperature or liquid natural gas temperature is not so low. But what happens at even lower temperatures is really a mystery for many engineers. And they want to ramp up this same rate of production of ships and of carrying devices. And I think this is a huge opportunity to see what will happen. I mean, this will really change our world here in the next 10 years. Of course, superconductivity is going to be a big theme in that, because at 20 Kelvin you have many superconductors which have very interesting properties. So this is for the motivation of superconductivity. Now, the point where the project starts is from Andreev reflection. So maybe I can remind you that the superconductor is made out of Cooper pairs, and actually we take one electron band and we replicate it with one hole band, and then we open a gap and we have a mixture of something which is electron-like and then goes over into hole-like, and here there is a gap which opens. So this is one of the basic aspects of superconductivity. Now, when superconductivity was found, one of the first experiments which they did is to measure the thermal conductivity. And the thermal conductivity of something which has zero entropy, like superconducting electrons, is zero, exactly zero. Now, they managed to make some material where the superconductor is interspersed by normal areas. And there they found that the thermal conductivity is also zero. And this was very puzzling. And Andreev, it's his photo in Miraflores, took this challenge, and he proposed one new phenomenon and one new thing which happens in superconductivity. And actually he realized that if you approach with an electron into something close to a superconductor, slowly the gap opens, the gap in the superconductor opens, and the electron slowly transforms into a hole because of the change in the dispersion relation. And then the hole is exactly retroreflected, and you have the Cooper pair which falls into that. So Alfredo and his colleagues, they have been working on this problem very nicely, and they realized that this is not just true, but it is also quite generic. And if you take two superconductors and you try to understand what happens in the interface, you have this kind of situation, but which happens many times and creates a resonance state which allows you to carry a current from one side of the junction to the other. So from our side, we took a look on this problem from a totally different perspective. So when you apply magnetic field, you have a vortex which nucleates in a superconductor. And this vortex provides you with a radial asymmetry, and it also provides you with states which are inside the vortex core. And these states can be also understood as multiple Andreev reflection, which happen from what happens here inside this small circle, this small thread actually, with the exterior. So these 2 points of views were kind of separated, and one of the things of the project is to try to see if we can make something together. So the basic technique which we use is STM at very low temperatures. So I think I don't have to go to the details. This is a very nice picture of how it works by our chairman. So you see that we have our current, and by measuring the tunneling conductance, we have a direct measure of the density of states. So when we measure the density of states of such a thing, we are going to get an anomaly here, and here inside we are going to get no states. And this is what we find when we take a look, for example, in aluminum. We have here the spectrum, which has no states inside the superconducting gap, and with this we can study superconductors. We need to go to very low temperatures and to have a high resolution in energy, and for this we have to make the hardware and the software ourselves in order to be able to do that. So we can have atomic resolution at low temperatures, and there are nice developments as made by Isabel, as we have heard this morning already, to be able to measure at very high magnetic fields. This is pictures taken at very high magnetic fields. So during the time using this technique, we have been studying many superconducting materials. So if you see here this gap structure, which you find in many different systems, and then you see that each one has its peculiarities. And this was kind of the basic tool which we have been using to develop this project. Now, of course, we have been also working in trying to get new materials, and this has been something which is relatively recent. And the idea is very simple. So actually, we start on a phase diagram, which may be very complex, and we search for places where we have a nice single crystal which grows inside the liquid. We get this single crystal with the liquid out of the furnace, and we centrifuge it to separate the single crystal from the liquid. And in this method, we can make many single crystals. And we have been making many different materials. Many of them are taken from the topological material database, which Juanjo showed us this morning. Of course, this has also helped our effort to study the superconducting gap. All these samples were gotten from somewhere else. Here, these samples here were made at IFIMAC, where we tried to understand what we were searching here for a layered superconductor and here for a topological superconductor, and went until the end where we made the experiment. Okay, so let's go for what I would like to say, what we have been learning, and in particular about these Andreev states in vortices and magnetic impurities. So let me go a little bit back. So when we have the superconductor, we have the creation of these Cooper pairs. Now, when we apply a magnetic field, the magnetic field destroys the superconductivity. And you can understand this destruction or this effect in two different ways. So first of all, you can think that a magnetic field acts as creates a Lorentz force on the Cooper pairs, and therefore it breaks the Cooper pairs. This is the electromagnetic mechanism, and this leads to the creation of vortices. Then there is the exchange interaction, which tries to align the spins which form a singlet. And these two mechanisms are acting in the superconductor. So in the first mechanism, we have this set of Andreev bound states which are located inside the vortex core. And there is one feature of this Andreev bound states, in which I'm going to insist later, is that actually the separation between the bound states is actually much smaller than the temperature. This thing here is the derivative of the Fermi function. And this situation is rarely attained in a superconductor. Mostly we have this situation. We have a bunch of states which are located inside the vortex. And even in spite of having a bunch of states, you can see an increase of the density of states, and you can follow this increase as a function of the position, for example, here in this material, which is highly anisotropic, and it has a star shape, and in this material, which is not isotropic, and you can follow this Andreev physics. Now, what happens if you have this exchange interaction? Now, people show that when you have this exchange interaction, you immediately see a very strong electron-hole asymmetry. And this is something which you can understand theoretically. And you see here peaks inside the superconducting gap, And there are peaks, you see that these peaks are located differently. There is a high peak here, a negative bias, and there is nothing, a positive bias. And when you plot this density of states as a function of the position, you see oscillations. These oscillations give you a length scale, which is the Fermi wave. And you can follow these oscillations and follow the physics which is behind these localized states. Of course, as said by Juanjo this morning, so you can follow these states as a function of the position, and you can see where you find Majorana fermions. My picture, my favorite picture, is to see what happens on the bound states inside the vortex core. So the bound states are, of course, given by the quantum mechanical energy. Now, if you want to make a Majorana state, you have to eliminate mass. If you eliminate mass, you eliminate this 1/2, which is the consequence of 0-point motion, and therefore you have a state which is symmetrical electron hole, and which is lying exactly at 0 energy, so a Majorana state. So there are people, of course, following this idea, and very soon in nature you will see someone who really claims to have found not just a Majorana state, but a Majorana lattice. I don't know how far this can be said that this is true, but at least there are efforts going in this way. So let us see what we understood in our work. So in order to work, we took these two examples. One example is a superconductor which is highly anisotropic, and a superconductor which is isotropic. So, and then we put magnetic impurities, in this case iron. When you're at zero field, you see these kind of small blocks in the images, which are each isolated iron impurity. When you apply magnetic field, you see nothing because there is no Kondo effect. The impurities just wash out inside the metal. Now, when you test on what happens with the density of states at local scale, you can see that there are kind of oscillations which go up and down here when you check the bias voltage, and this means that at every position there is a high electron hole asymmetry. And this is characteristic of the states which are created in an iron impurity. And you can follow this as a function of the position and extract the decay length and extract also the Fermi wavelength, which is given here, and so on. Now, we have been making, together with Jose in Valencia, density functional calculations to exchange the iron by the niobium by iron and see how the magnetic moment looks like. So here, this is this system. Here you see that there is a little disorder because some of the selenium are substituted by iron, by sulfur, and you see that the sulfur is located randomly here in the image. And this has a consequence. These two guys here, which are located in these layers and which were just thrown randomly by the calculations, they actually make that the symmetry of this problem is no longer 6-fold, but it is just 3-fold. And this can be also seen in the experiment. So we can understand to a pretty large way what happens around one of these magnetic impurities. Now, what happens if you have a vortex? Here you see here you can see the length scales, which are really different. So this bar is the same here and here. And here you can see that the vortex, well, there is this bunching of states which gives this peak at the Fermi level, and this peak evolves as a function of the position. When you have a Shiba state, you also have an evolution, but it is electron hole asymmetry, and the distance is given by the Fermi wavelength. Now, when we have vortices and Shiba states, we realize that when you take a look on the electron hole asymmetry of the images, there is a little difference which pops up in the images. So the insight came when Alfredo and Sungun studied this problem, and they realized that actually there is a connection between the Shiba states, the bound states which are located in the Shibas, and the bound states of the vortex core. And this connection gives you actually a slight asymmetry in the wave function. You see that these two are not exactly equal. Here there is an impurity located here, and the vortex is located here. In blue is along this direction, and in red is along the other direction. So there is a slight asymmetry because there is an impurity here. Now, this happens when the Fermi wave function is relatively sharp with respect to the interlevel distance. Now, when the interlevel distance is small or the Fermi wave function is broadened, actually, of course, destroy all these waves and the whole signal is killed. However, the electron hole asymmetry remains. If you go in one direction, you have something which goes like this. In the other direction, you have something which goes like this. So actually, as Alfredo noted, this electron hole asymmetry is related to the band structure of the superconductor, and is inverted if you have electrons or holes. So the whole thing works. You have kind of a quantum property, which is the electron hole asymmetry, which transfers to very large scales in a system which should be, in principle, very much smeared by temperature. So, of course, this can be made by putting the impurity further from the vortex core, and you see that the size of the signal decreases. If you have anisotropy, then you have different states. Now, what was very nice is that Moon and Alfredo, they made really a map of all the impurities which we found in our experiment, and they managed to calculate something which really looks like, given the circumstances, very much what we find in the experiment. Not just in a system which is isotropic, but also when you have a significant anisotropy. So when you have no impurities, of course, nothing like that happens. And when you have different vortex cores, each one has its own impurity concentration around it, so the effect will be different. So essentially, what we have learned, as I have said, is that with such a situation, we can transfer this electron hole asymmetry to a much larger object like the vortex core. Now, this has some consequences, and actually we have been studying a system where you actually increase the number of impurities, and you have this electron hole asymmetry, which is vanished when you increase the number of impurities. And in that case, when the whole thing becomes much more electron hole symmetric because of the Shiva impurities, the vortices also become symmetric. Now, if you take a look on a system which is very close to a quantum critical point, like this one here, you have also Shiva states. This one is a D-wave superconductor. The states here are of different nature, but you have them. And these Shiva states give you an electron hole asymmetry that is again transferred to the vortex core. So it is something which probably will happen again and again in superconductors, and it is something which was kind of nice to learn and to find out. So how much time do I have? Okay, great, thank you. So let me also show you another example where we obtain some insight, which is in a heavy Fermi. So in 2019, we had, Felix is no longer there, but we had the year of the periodic table. So people in the journal here, they gave the periodic table to the family, and they realized that actually they were looking mostly at this point, which is a pity because we lose the rare earths. And the rare earths are, of course, very interesting. And they propose that we should actually place to all our students the periodic table upside down. Okay, so in order to highlight the importance of the rare earths. So this nice exercise shows us that the rare earths are important. And actually the last ion or atom which you can handle in a lab is uranium. Uranium in a tetragonal structure here in uranium, ruthenium to silicon 2 provides you a huge amount of internal degrees of freedom, so large that there are still many mysteries associated with this nuclei. So in this system, in this when you put it in this structure here, you have actually a transition here, which is a mystery. So no one knows what is this transition. It's probably some sort of multipolar order which happens in the uranium nuclei. But you see that it takes a huge amount of entropy. Now we try to study this with the STM, and as I said, we have the density of states, which is we have the tunneling conductance, which is proportional to the density of states. But here we have a system which has F electrons, and F electrons are very peculiar. So when you have F electrons, actually the whole tunneling process changes. So you have to consider that you may tunnel into an F electron, or you may tunnel into something which is not an F electron, an SG electron. And this opens two conduction channels which are in parallel, and these two conduction channels are going to interfere. And the interference will be give you as a result a Fano anomaly. Now this happens if you have a single impurity or a single ion where you have F electrons. If you put a lot of F electrons, as in the lattice, then you have what we call a Kondo lattice. So you use Anderson's model, and it happens that in that case you have a heavy band, a very flat band because of the F electrons, and then you have somewhere else a usual band because of the rest of the electrons. These two bands at low temperatures through a many-body interaction process hybridize, and through the hybridization they create a situation where you have very strong band bending and also a high density of states at the Fermi level, and this is identified in the feature in the tunneling conductance by this kind of features. And this was made in many different compounds. So for example, serum cobalt 5, here again serum cobalt 5, uranium tellurium 2, or many other things. And you see that these two systems here are superconducting as well as uranium ruthenium to silicon 2. However, the signal which we see in the superconductor is extremely small. This is just a very small fraction of the whole density of states. So all these materials are triplet superconductors. So if there is a Majorana fermion, this material in particular is a triplet superconductor. This is a D-wave superconductor. But if there is a Majorana fermion, it will pop up at the surface of this system immediately. Now, how are we going to identify something interesting at the surface related with Andreev reflection or whatever if the gap is so small? So we thought, okay, we have to understand this. So, as I said you, in many other compounds, the gap is fully open and it's not as small as there. So, if you take a look on the specific heat of all these compounds, those of you who know the specific heat, this goes down practically to zero. So this means that the bulk is really superconductive. There is no way out. So this is a puzzling situation, and we set up to try to understand that. So in the uranium-lutetium to silicon 2, you have these Fano anomalies here. Then there is a gap opening here, which happens below this strange phase transition. And inside the gap opening, there is again a very small superconducting gap. When we make the experiments, we realize that if you take a look on the tunneling conductance along different terraces, and you plotted this in such a nice color scheme, then you see lots of small anomalies. So what is the origin of these anomalies? So, of course, in metals, you can have places where there are no states in the Fermi level. And in these places, you may find the surface state. So the surface state in copper gives you this kind of reflections and nice things, which you can then shape to form a quantum coral. And these have their own properties, so they have the width, and when you confine them, you have again confination, and you have the different quantum levels, and you can follow this physics by taking a look on the spectra in an STM. So what we have found here is actually a consequence of the quantum confination, but it is a very peculiar quantum confination. So here you see that we have confination, okay? So we have different levels, and you see that these levels have a certain width. So they have a certain width because they are sensing the electronic correlations inside the bulk. And this gives this width here. So by making very long terraces, we could make this width, the difference between the quantum levels, very, very close to each other. And then we could eventually match to superconductivity and see what happens there, and see if this may change the superconducting properties as I have proposed earlier. However, in that case, the width would be very large. This is hundreds of millivolts. So instead here we have something which is just a fraction of a millivolt, and you are going to see this in more detail. So for example, here we take one particular terrace, and we have here 4 states, 5, 6, 7, etc., and we have the level separation which is obtained here. By removing the background, which is due to all the anomalies which happen in the bulk, we can obtain actually the level quantization. So we really see that we have quantized levels, and what is here very peculiar is the dispersion relation of these quantized levels is 17 times the free electron mass. So we have here very heavy electrons, heavily correlated electrons, which provide us our quantum level. So this is fundamentally different from what was made in the case of copper. We can follow all the physics, like making with the Fabry-Perot expression. We can make all these nice fits. We can also calculate the reflection coefficient as a function of the bias voltage, and this is what happens in copper. You see that it's a very flat dependence. Here in a very short energy range, we have a very strong dependence. We can calculate how the spectra look like as a function of the position and fit it pretty nicely. And then we can also extract the lifetime, so the width of these levels. And we see that the width of these levels corresponds to really very strong correlations, which is the heavy masses which we have on the bulk, which is due to the heavy masses which we have on the bulk. So this reflects the connection between the 2D heavy fermions and the bulk. So when we continue, we let me see like this. We of course we need some band structure calculations to see what happens here, and I would like to show you this here is actually very well reproduced by the experiment. This is one of the few F electron systems where you can use DFT, and here there is a gap, and we contacted the people who have made this calculation, and actually they made a nice lab with the uranium atoms, and they found that exactly at this position here there is a very shallow band with a mass which coincides with the mass which we observe in our experiments. So then, once we had such a two-dimensional heavy fermion situation, we have to think of how to understand the tunneling spectroscopy in that case, and then it came the idea that the best way to describe that would be to see if we tunnel a relatively we tunnel step by step into the two-dimensional heavy fermions, and which are proximity superconducted by the bulk. And of course, these two-dimensional heavy fermions are connected to the anomalies which are located at very low energies and which actually snare the superconducting gap features. And using this, we can understand what is going on. So I think with this, I come. Am I in time? Yeah. Yeah. So I come to the conclusion. I would just like to stress. I have just shown two examples. There is one 13-portaling example. So you know that there is a DC Josephson effect. You also know that there is an AC Josephson effect. Well, there is something new. Oops, sorry. And we have discovered this in a very small Josephson junction. So it's a sort of a feedback-driven Josephson effect, which happens in a frequency range which is totally different than the usual AC Josephson effect. So what we learned from this is, well, as I have shown you these two examples, and we are working on understanding what happens when you go from an isolated impurities to a set of impurities, what happens in the Nick-type superconductors, and what happens if we have Shiva states from other systems. Of course, we are trying to measure uranium tellurium too, which is a very hot topic and very hot material now. And we have been working in heterostructures of the ferromagnet and niobium. And the AC Josephson behavior is also very promising. And I think with this slide, thank you for your attention. I hope to have shown you that we have gone over to a situation where we have a set of works where we can work together. And just finishing, so recently we got a new cross-action in the field of superconductivity and quantum materials. So of course the cost actions are very open. So whoever is working on the field is invited to use this cost action in the best possible way. So thank you very much for your attention.
Hermann, so we have time for a couple of questions.
Concerning the uranium ruthenate, maybe you explained and I missed. I didn't catch what is producing the confinement that you have shown in your experiments. Is it the eraser structure that we have at the surface, or is something else?
It is the step structure. It's some sort. So we have been searching for places where there are steps with a relatively small. So not very large flat areas, but steps which are relatively small. In that place, we identify the oscillations corresponding to the one.
To have that, you need a relatively regular sequence of the steps, at least of some range. I mean, with the same spacing. Otherwise, you would get different confinements, and you would not get this well-defined state.
Well, it depends on the reflection, right?
I guess that with a single step, it would be small. If you don't see, well, maybe you are confined, strictly confined in one step, in one terrace. Maybe there is no interaction between neighboring terraces.
No, there is some interaction.
Then there should be regular terraces.
They are more or less regular. But actually, the same path is active.
My second question: how are you preparing the surface of this crystal? It's just poly and cleavage in low temperature.
Yeah, this is very important and it's very tricky. So actually, you need to have perfect surfaces, of course. And what we do is we pull at 4 Kelvin or below, and then we actually ask the people who make the crystals to make long crystals like this one, and then we break it like this at low temperatures.
I understand that this is the all one direction.
Yeah.
Looking at the unexpected direction.
Yeah.
And final question, sorry.
Yeah.
Usually it's difficult to work with uranium because there is some fraction of radioactive uranium. How are your crystals?
Well, yeah, you can see, well, I don't draw the photos, but these are really tiny. So the difficulty is to grow these crystals. And this, of course, is something which we are never going to access. This is made at Tohoku and in Grenoble.
We have several questions in one, so maybe we'll have time for a very last one. If there's any.
So in the Fano resonance that you showed, usually to get the Fano resonance, you need 2 channels that lead to the same final state. So it's a very naive question. What's the final state here? Can we go to these X orbitals and to the other orbitals, but then where does it end up interfering?
Yeah, that's a good question. Actually, well, it's the bulk, right? So you tunnel into the surface. So it's the state which you find there. Well, if there is a single impurity, then you tunnel into what surrounds this impurity. If it is a heavy fermion, it's more tricky to understand.
Okay, let's thank Hermann again for the very nice talk. Well, this closes the session, and I pass the word to Rubén.
We are closing the session. It has been a long day already. Quite warm, not only the discussion. So I will take just a few minutes to tell you a little bit about some ongoing developments at IFIMAC. Some of them have appeared this morning already in the opening session. So what I want to share with you is actually something that we were discussing. We have an IFIMAC council a few days ago. And we were discussing this, and I want to share it with all of you, also with PhD, with postdocs, with all the people who actually made what IFIMAC is, which is, as you have seen this morning, is a real success. And what we want is actually to set the foundations for the future, for the next 20 years. So, talking about the current activities, it was already mentioned this morning in this mentoring program for female students. The record was talking about this. We have set up this program as a first experience. I think we have been very successful. We have attracted already 27 students who want to be enrolled in the program, and we have managed to attract 30 mentors, which is already an achievement as well. There will be some kind of training for those mentors, and we will start with this for the next academic year. And the idea is that based on this experience, we will continue with this program, probably also in collaboration with the rest of the university. That could be like a pilot experience that probably will benefit the rest of the university as well. Then there is, because if you look at the webpage of IFIMAC, you already see that we have prepared some nice videos over the years. We have actually presented the project to the FSC and got finance. So we have plans to produce another 3 videos in the next year with 3 different topics: quantum technologies, advanced materials, and the physics of life. And we will hear more about this, and actually we will need some support from some of you to develop these videos. This is an initiative that we will do in collaboration with Quantum Fracture, as we have done in the previous videos, and we hope that actually that will help us to raise the profile of IFIMAC. In the same direction, when the pandemic arrives, we stop our in-person seminars. We have managed to set up these online seminars, which are working extremely well in collaboration with the Institute of Material Science. We plan to continue those, but also to come back with real seminars, in-person seminars. So we will have one, at least, of those a month. And there is already a committee who is going to prepare the program for those seminars for the whole academic year. And again, they will ask you for suggestions for speakers to be invited to those seminars. And finally, there is a communication committee who we recently established, and it has been already working very hard on this IFIMAC Day. Recording the talks and also tweeting what was happening here. And again, we have plans for that. We have the idea
to collaborate, to raise our profiles on the social media, but also to set up some internal communication channels, like a newsletter. And again, we will need help and support from all of you to provide information to that and to actually circulate and make this information to reach all interested farmers. And finally, the word about IFIMAC's future. As you were listening this morning to the rector, she said that IFIMAC was a success. And I think it's true. We are the only institute, the only research institute in the whole university which has this recognition as Maria Maestri. We got 2 of those, which is an even more rare thing. But in order to continue with this path of excellence, we need to move forward. And actually, since I took over in the direction of the institute, I have been trying to push in 2 different directions. One is to try to change the legal status of IFIMAC. We plan, and that's the idea that we have agreed with the university. We are working already in the direction of setting up an IFIMAC Foundation that will be the host of IFIMAC, with the idea that that would help us to be much more effective in the way we can attract funds and the way we actually manage those funds. So that's the idea. With that, we'll be able, with that legal status, we'll be able to apply not only to Maria Maestri, as we can do now, as a center which depends on the university, we'll be able to apply to a Severo Ochoa recognition, which I think is something that we have a scientific potential for getting that, but we don't have the legal status for doing that. So this is one of the aspects where this would benefit. And the other thing is that you know that we have pressing needs of space for both labs and offices. And there was a project to actually refurbish some spaces in the module C5, both from in the basement already we got some labs, to finish up that basement and to do something in the ground floor and in the first floor, to accommodate space for labs and for offices. This is something that requires a lot of money. To refurbish something that is already built requires more money than to do something new from scratch. And the university doesn't have that money, and we cannot attract any kind of funding for doing that. And actually, the solution that we have got for that is that, again, through the university, we are going to enter a private-public partnership where there is a private company that is going to build a brand new building, and one wing of those buildings will be devoted to IFIMAC. So we will have a brand new building with new facilities, with more space, mainly for labs, but also for offices. And the idea is that that will be the basis for the IFIMAC of the next 10, 20 years. So this is something, this is an ongoing thing. We are, the university has already reached an agreement in that direction, and we are in the first stages of designing what will be the path of that building that will be devoted to IFIMAC. So this is something that, as I'm saying, is still ongoing in both aspects, but I wanted to share this with you, to show you that we have been successful, but anything has to move. I mean, you cannot stand still in science. You have to move forward. You definitely move backwards. So those 2 things, those important things, will help us actually move forward in the next 5, 10, 15, probably 20 years. So thanks again for coming to this IFIMAC Day. This is something that we have made for the first time this year, after 10 years. Our plan is to do it every year from now. So we'll have the opportunity not only to learn about what we have done already the previous year, but also to hear, to listen more to what we are doing right now. We have done this year through the conference session, but next year we will have also talks telling us about the cutting edge science that we do at the IFIMAC. So thank you again, and enjoy the rest of the day.